Hi, my name is Shivam and I'm presenting the work titled Spatio-temporal Analysis of Multi-Agent Scheduling Behaviors on Fixed Track Networks. This was done in collaboration with Günter Wallner, Jeremy Watson, and Fabian Beck. In many multi-agent scenarios, agents are scheduled to move on fixed tracks from point A to point B. In these cases, visualizing the spatio-temporal attributes can help to understand agents' actions, their interdependence, and the coordination between them. This in turn helps to optimize their behavior. We take a specific example of a multi-agent scenario. Flatland is a simulation environment for developing scheduling techniques. It offers several maps with varying sizes. Each map has a fixed track rail network. The number of trains to be scheduled grows with the size of maps. As shown in the playback, the trains can move forward on a fixed rail line and travel at the same speed. Trains can also experience random malfunctions during their journey, which restricts their movement for a few time steps. As backward movement is restricted, head-on collisions of trains results in a deadlock. Various competitions at conferences have been organized to explore new scheduling techniques. The goal is to schedule a maximum number of trains to reach their destination in minimum time across several maps. To improve the performance of developed scheduling technique, the experts need to understand their behavior. Usually, the experts rely on watching episode playbacks like this. However, it is challenging to do so from the playbacks. In this work, we focus on visually analyzing movement and scheduling behavior for the Flatland environment. Most similar to our approach is Mosaic Viewer, which proposes a timeline visualization to show the activities of each agent in an individual row, and a graph showing communication among agents. However, Mosaic Viewer focuses on investigating the agents' activities when they are not synchronized in their worldviews. The Murray graphs dating back to the 19th century shows transit schedules by plotting distance against time. They are appropriate for visualizing the movement with respect to a single line, but cannot visualize the movement of several trains in a complex network at once. Mobility graphs address the issue of scale and focus on representing aggregated movement behavior. It includes a node link diagram that shows the movement between semantic places. We use the concept in our approach. However, our aim is also to enable a detailed analysis of individual agents. Before designing our approach, we interviewed 3 Flatland experts. The first expert had a main role in organizing the competitions. Second expert was affiliated to the Swiss Federal Railways, a Flatland partner, and analyzed the scheduling behaviors of trains in Flatland, as well as substantially contributed to the code base of the environment. The third expert is an artificial intelligence professional affiliated with the German Railways Company, also a Flatland partner, and explored agent-based scheduling techniques in Flatland. Based on the interviews, we derived 5 specific analysis goals. They are getting an overview of train schedules, analyzing resource utilization in the rail network, and assessing path efficiency of trains. It also includes investigating the cause and effect of issues such as deadlocks or malfunctions, and finally, exploring the scheduling strategies through the collective and simultaneous movement of trains. An additional requirement resulted from the later expert feedback, comparing train schedules between the 2 episodes. We propose a visualization approach consisting of 3 linked views, providing different perspectives on the train movement data. In Flatland, an episode is one run of the Flatland simulation on a map using a specific scheduling algorithm. Enabling analysis of a single episode, we implemented the first version during the Flatland 2020 NeurIPS Competition and collected feedback from a diverse group of experts. Based on the results, the approach was further extended in the second iteration after the competition ended. The extension included a feature to compare two episodes simultaneously. The prototype includes the dataset of winning scheduling techniques from the competition and can be selected from the episode selection panel. The line chart shows their performance across different maps. We use blue and orange colors to show episodes A and B respectively. Icons show the end status of each train, the ones that reached their destination, those that were still on track, and finally the ones that did not even begin their journey at the end of the episode. We show each train in a row, while the horizontal axis becomes time. The trains are grouped according to their end status. Within each group, trains are ordered based on their starting time. The departure of a train is encoded as a black ring, while a filled gray circle denotes that the train reached its destination. Since trains mainly make route decisions at junctions, we also encode reaching a junction by a diamond shape. Movement is depicted as a colored line. Malfunctions are represented by a colored cross with a tail, where the length of the tail denotes the duration of the malfunction. We detect simple cases of deadlocks, represent them as colored squares, and connect them to other trains involved in the same deadlock. To assess the path efficiency, we compare the lengths of actual and shortest paths. The actual path length is shown by a horizontal bar, while the bars for the shortest path length are colored in green. For trains that did not reach their destination, the actual path length might be less than the shortest path. To avoid confusion, we show these actual path length of trains on track by an unfilled bar. While comparing two episodes, the visual encodings are preserved. Each row in the timeline view is split into two. The top represents the train events from episode A, while the bottom shows the same for episode B. The map and graph views provide a spatial perspective of train movements in the rail network. A heat map highlights the utilization of each rail tile. Different regions can be of interest during the exploratory analysis. Hence, we provide two modes of region selection. The first mode is a rectangular selection. The second selects a rail segment between two junctions. To analyze the abstracted movement, we integrate a graph view in our approach. It contains a directed node link diagram where a node represents a selected region, while movement between regions is represented by the links. The node size indicates number of trains visiting the region. The width of a link represents the number of transitions between two regions. Regions not traversed by any train are represented by unfilled circles. The region selection works similarly, with consistent usage of colors while comparing two episodes. We collected feedback from 10 experts in the fields of operation research, artificial intelligence, and information visualization. We analyzed their responses. The results mainly indicated that the visualization is helpful to analyze the train movement behavior of a scheduling technique. In their feedback, the experts requested a detailed simultaneous comparison among two scheduling techniques. Hence, we extended our approach in the second iteration, enabling the comparison of two episodes. For details on the feedback analysis, please refer to the paper. We apply our approach to analyze the submissions to the Flatland NeurIPS 2020 competition. We select one of the top reinforcement learning solution for our analysis next. Overall statistics at the top shows that 5 trains were still on track. At the bottom, we can see that all 5 trains were involved in a deadlock. Focusing on the 2 trains, using the playback controls, we navigate to the time before the deadlock occurred. The 2 trains headed towards each other in opposite directions on a single track, which led to a deadlock. Knowing about this ineffective coordination in a specific scenario, suitable techniques can be used to improve the performance. For example, better agent observations or communication among agents. Later, the deadlock propagated and affected the other trains. Next, investigating the path efficiency of trains, we observed that few trains followed a longer path to reach their destination. We also see that 2 deadlock trains have followed a much longer path. The trains experienced malfunctions twice that could have altered their originally intended route. To assess the parallel track usage, we select 3 regions. 2 tiles on each of the parallel tracks R4 and R5, and a common connecting tile as R3. From the aggregated graph, we observe that the reinforcement learning approach inefficiently used only one of the 2 parallel tracks between R3 and R4 to move trains in both directions. Details on other discovered insights can be found in the paper. Based on our experience, we reflect upon lessons learned. First, preserve a static map of temporal behaviors. While analyzing the interdependent behavior from spatio-temporal attributes, a change in point of view challenges the mental map of the analyst. As a result, during the analysis, it becomes difficult to remember the attributes of multiple agents simultaneously. We used a fixed timeline to show the actions of each agent in rows, with meaningful grouping and ordering of trains. This helps to construct a mental map about multi-agent behavior, while interactions with the interface provide details without changing the overview. Next, interactively define spatial focus and map it to time. Many spatio-temporal visualizations, including our approach, have separate views for each attribute with linked interactions. However, to study group behavior in multi-agent scheduling scenarios, they are not enough. We learned 2 things. First, domain-specific encodings and interactions help the analyst to focus on specific regions. Second, showing the effect of spatial selection on temporal dimension helps reveal unexpected insights. For instance, on hovering over the selection of a region of interest in the map view, gray semi-transparent rectangular boxes are drawn in the timeline view. This leads to insights such as cyclic movement of agents, as exhibited by train 10 through region R2 in the figure. Finally, we learned that abstracting the exact movement of agents over user-defined regions of interest helps. It allows focusing on movements between selected regions. Generally, the abstracted and aggregated representations are put first in top-down exploration. However, in multi-agent scheduling behavior analysis, we realized that a bottom-up exploration was first necessary to identify relevant specific agents and regions of interest. We presented a visualization approach to analyze spatio-temporal scheduling behavior on virtual fixed-track network. The encouragement and support from the Flatland community prompted us to release the tool for all competition participants and can be accessed via this link. Future work includes integrating the planned modifications in Flatland competitions, for example, varying speed of trains and time windows to start the trips. Thank you for your time and attention.